I'd like to thank the organizers for giving me the opportunity to speak in this wonderful meeting. Actually, there are two reasons I have chosen this topic, and first one is a bit superficial. Okay, I wanted to have something to do with this title, and I think I have managed to get almost all of it. It's an out of equilibrium system, although I have not mentioned it explicitly, so I think I have managed to get almost 100% of the title. The second reason is, it's the main reason. Since this is a meeting which is celebrating this Indo-French collaboration, so I thought I will showcase some work which actually came out of this collaboration. And these collaborators are Satya and Manas, both are there in the audience. They are also organizers and also the PIs of this project. So this is resulted in two publications. The first one is about this classical problem with Satya, and then second one is about this quantum problem, which is with Satya and Manas, and it should come out soon, either this year or next year. So let's start with a problem which all know, like equilibrium systems. So in equilibrium system, it's described by this energy functional. So this configurations is defined by some these coordinates. So you can just think of it as like a position of a gas particle in a gas. Okay. So this potential, this energy function has a like confining potential, single particle term, two-body interaction, three-body interaction, and you can put anything you want. Irrespective of whatever the energy functional, you know that the equilibrium probability distribution for the joint probability distribution of these coordinates is given by this Boltzmann distribution. Okay. And given this distribution, one is usually interested in calculating various micro and macro observables. For example, you might want to ask what is the average density profile of the gas. Okay. What are the correlations? That's something people are interested in. And nowadays, there is also interest finding out these extremal properties. Like for example, you can ask, there's this gas, what is the age fluctuations? Okay, so you can ask, okay, what is the fluctuation of the rightmost particle in the gas? Okay, and in general, you can ask about order statistics. For example, if you ask the kth particle from the right, what are the statistics of this particle? People are interested in gap statistics. So again, you can ask what is the distribution of the gap between, let's say, kth and the k plus 1th particle, and full counting statistics. So it's basically the statistics of number of particles in a given region, and you can take this region for simplicity to be minus L and plus L, but you can generalize it. So these are some of the observables interested, but you can ask, you can consider any other observables. Okay. So if the system is non-interacting, where your two body or any higher body interactions are not present, then this joint distribution is of course very trivial. So it has this product measure where it factorizes into single particle distributions, and where the single particle distribution is basically the single particle Boltzmann distribution. So in this case, these variables are IID random variables, and for this ideal gas, all these observables which I have mentioned above, these can be calculated very easily. Okay, these are like a very simple questions. Okay, if you have interaction presence in the problem, okay, although you know this joint distribution, which is a Gibbs distribution, the computation of this observable is usually rather hard. And when I say interacting, I mean strongly interacting system. So except one case where many of these observables can be computed, although the calculations are quite hard usually. So this is called the so-called rich gas, and I think somebody mentioned it already. I think Kiran, you did probably, yeah, during this conference. Okay. So these cases, basically many of these observables can be computed explicitly, and many of these people in this audience actually are involved in calculation of this observable, like Abhishek, Manas, Anupam, Satya, Gregory, and many of their collaborators. So this is one example of strongly interacting systems where you can calculate this observable, but these kind of examples are rather rare actually. Okay, if you go to non-equilibrium system, it's even harder because you don't even know often how to calculate this joint distribution, and unlike this equilibrium, this joint distribution is not a priori given, and in some cases, even if you know the joint distribution, this calculation of these kind of observables are rather difficult. okay, because there is no general prescription for doing this kind of calculation. Okay, so if you go to the quantum domain, again there are very few examples where you can do exact analytical calculations. For example, nowadays people are interested in interacting bosons because they can be realized in cold atom experiments, and usually this people use this model. We have already heard about this Liebniz model where these bosons, they are in one-dimensional this thing and they interact via this delta function potential. So in this case, okay, you know the solution for the free case, it can be written in form of Bethe answers, but if you put a potential, it breaks the integrability. So for any experimentally relevant situation where usually you have a optical trap, so this doesn't work, okay, so you don't know the answer. So similarly, when this Gross-Pitarski equation, where again it describes this weakly interacting Bose gas, so if you put a potential, these analytical solutions are very difficult. So all these experimentally realizable situations where you usually have an optical trap where your system is there, they are very, it's very hard to do, very hard to find a model where you can do analytical, okay. So the moral of the story is that, okay, so there is a possibility of analytically tractable model for strongly correlated gases in both classical and quantum regimes, okay. And even if a solution can be found in some cases like this Liebniz model without the potential, this analytical calculation of this observable kind of observable I mentioned, it's usually rather hard, okay. So there's a growing need to engineer analytically tractable models for correlated gases, and when I say correlated gases, means strongly correlated gases, both in a quantum and the classical domain, where you can do calculation and also these are experimentally feasible. Okay, so before I talk about engineering these systems, so let's just ask this question: like, I mean, why are non-interacting systems are easy to deal with? And answer is very simple, because in a non-interacting system, the joint probability distribution is, you can write as a product of this individual probability distribution. So it has this factorized form, and this factorized form, which is this IID form basically, which makes analytical calculation easy. Okay. So then question is, can we engineer a correlated gas, strongly correlated gas, that retains this product structure somehow? Okay. So it might sound contradictory, self-contradictory, because if I say that, okay, if you have this product structure, it is non-interacting, but then I want to build a strongly interacting system keeping this product structure, right? But the answer is actually yes, you can do that, and answer is this one, okay? So of course I can write down a joint distribution of this form, okay? So I can write down, I have a product structure, something there, and this is characterized by some parameter u, okay, and I average over this parameter u, okay, and this p can be anything, okay. So I can just write down by hand, but that's not the point, right? Can I realize a system which has this product structure? So can I have a system which I can realize experimentally or physically, which gives this product structure? And this is this structure. There is a class of model recently it is found. So this structure is called this CIID structure, conditionally IID structure. Basically you have a IID structure inside, conditioned to some parameter u, and you average over u. Okay. So it turns out that you can actually find this kind of structure by on physically realizable models, and this first model was this a model of resetting Brownian motion. So we have already heard, I think 2 or 3 talks about resetting Brownian motion, but here instead of one particle, what you do is that you have large number of particles and particles, and it let them evolve independently, but then when you reset them all together at the same time. So you simultaneously reset them, okay, and then again they evolve independently and you simultaneously reset them. So this simultaneously resetting process creates a strong correlations among these particles, and that results in this structure, particular CID structure, where this H of u is given by this and this P of x is given by this form. And this is a work done by Satya and Gregory and their collaborators. So there is a second example, so where again you take this large number of Brownian particle in a harmonic potential. So these are non-interacting Brownian particles. So if you just don't do anything the system has a product measure. So now what you do is that the strength of the trap, you basically change between two values mu1 and mu2, and the time, okay, it's there at some mu1, and then you take a time drawn from an exponential distribution and then shift to mu2, and then let it be there for a time tau that's drawn from an exponential distribution and shift it to mu1. And you basically keep shifting between mu1 and mu2, and this again, this simultaneous drive, okay, creates a product structure, creates a CID structure which looks like that, and where this HU and this PU, these are given by. So this, in the first problem, actually this structure was almost evident immediately, but the second problem, it was in fact a very hard calculation. This is a problem, this Manas, Satya, Gregory, and this Marco Biroli, they did. So this structure was not immediately evident, in fact. So it actually came in a very roundabout way. I think finally they found some integral representation of some Kumar function or some such thing, but it's not evident that, okay, finally this, okay, it's evident that, okay, there will be some correlation, this will generate some correlations, but whether it will result in a structure like that was not evident at all, okay. So therefore, what are the necessary and sufficient conditions to have a structure like that? So you can have a strongly correlated system, but you can have a very complicated joint distribution, then it's very difficult to do calculation, okay. So the point is that what kind of driving gives rise to this kind of structure, okay. So answer is, okay, we have some understanding, but we don't have a full understanding. So therefore, it's good to study models where you can see that, okay, this structure emerges basically, okay. So this is what we did basically in this work, and in this work means basically I am referring to these two publications. So we find two experimentally feasible systems, one in the classical domain and other in the quantum domain. So where again a common and simultaneous drive drive the system to this kind of structure, and it generates correlation dynamically among these particles. So dynamically in the sense that if you don't do the drive, this is a completely non-interacting system. Because of this drive, it generates this correlation. So these are dynamically generated correlations, okay. And in both cases, the joint distribution had this CIID structure. Again, if I remind you, CIID means that, okay, it's like a IID structure inside an integral with respect to some parameter u, and then you average with respect to this parameter h of u, okay. And this h of u, okay, it depends on what kind of model you are looking at this. But the point is that if you have a structure like that, you can calculate many of these observables very easily, or you can actually, this becomes an analytically tractable problem. So this adds to a box of problems, basically of systems, of strongly correlated system where you can do analytical calculations, okay. The first problem is the classical problem. So what we do is that you take a harmonic trap and you put large number of classical particles, Brownian particles, okay. These are non-interacting particles. So if you just keep the trap, you know that the joint distribution is just factorization to single particle distribution, and you know that, okay, if you leave a Brownian particle in a harmonic trap, it's a Ornstein-Uhlenbeck process, so it will basically reach a steady state. So joint distribution is basically a product of this steady state Ornstein-Uhlenbeck process. But now what you do, you shake the trap. So where all these particles are there, and what I mean by shaking the trap is that you take the position of the trap, and you basically, the position of the trap undergoes a stochastic process, okay. So this is basically your energy function, and for each particle, this is the dynamics, where z of t is the position of the trap, and the z of t undergoes another independent dynamics, stochastic dynamics. And so for the time being, that this stochastic dynamics can be anything, but if you want a steady state, basically, okay, you should have a system where z of t always remains of the order 1. So it doesn't grow with time. So in this case, you can again find out the joint distribution explicitly at any time, in fact, and which has this form where this p is given by this, and this h of u is the probability density function of this variable u, which has this dynamics. Okay, so u has a distinct process, and the z of t is still arbitrary at this point, basically. Okay, it can be any process, and if z of t remain of order 1, In that case, in the limit t going to infinity, it reaches a steady state, and where the steady state is given by this. Okay, so where this is this IID thing, and this h of u is the steady state distribution of this process. Okay, so I want to note you that you might think that, okay, I have this trap, and this, okay, trap center is z of t, and okay, this particle is basically concentrated around the center z of t. But you should know that this is not the z here. It's another variable u. It's an auxiliary variable u, which is coming out of this another stochastic process basically. Okay, so it's not x minus z. It's some Gaussian around x minus z. That's what you would have imagined. Okay, if you do some adiabatic. Okay, you can, given this structure, of course, you can also compute the correlation very easily. And what you find is that, okay, you have a positive correlation for all-to-all particles. So you have an all-to-all particle correlation. Okay, so a representative example, you can have a telegraphic noise. For example, you can have a trap which just moves between two positions, like it just keeps going like that. And the time between this thing is drawn from an exponential distribution. So this equation in that case is basically the same of a run and tumble particle in a harmonic oscillator, and you know the steady state this thing. So this is the h of u for this process. You can also take this z to be an unstable process. Then in that case, the steady state of h of u is given by that. But you can take your favorite example for z of u, and it will generate a new h of u basically, right? The point is that for any h of u, basically we have a structure which is the second problem is a quantum problem. So where what we do, so you have a harmonic potential centered at x equal to plus a, and you have large number of non-interacting bosons. Okay, so these are non-interacting, and you cool the system so that they are in a ground state. So we start with a ground state of this Hamiltonian. So this Hamiltonian is basically the Hamiltonian of these particles in this potential, and you cool it to the ground state. So now what you do, you instantaneously you shift the Hamiltonian from here to here. Okay, you quench the Hamiltonian from here to here. That's equivalent to basically moving the trap center from minus a to plus a to minus a. So you just change the trap center and let the system evolve unitarily. Okay, this is a unitary evolution. The time for which you want the system to evolve, that's a random variable, and that you draw from this exponential distribution. And at the end of this time, you reset this wave function to the ground state of this potential. So this is, you can think of it like in experimentally, basically you shift the trap center to again plus a, and cool the system to the ground state, and you assume that, okay, the time taken to cool the system is basically negligible in compared to the experiment. And then you just keep repeating this. So you put it here, cool it there, and then move the trap there, let it evolve unitarily and for some time tau, and then you again quench to the ground state, and you keep doing that. And this repeated quenching to the this Hamiltonian and then resetting to this ground state drive the system into a non-equilibrium steady state. And in this non-equilibrium steady state, basically, if you look at, so how does it work? So if you you have this unitary evolution during this time tau, which is drawn from exponential distribution, and for this time, okay, you can write down this density matrix, and as in the classical stochastic resetting, here also you can write down actually evolution of density matrix in the presence of resetting. This is the work done by Christian Du, Satya sometimes back, and then once you have this, you can write down the quantum joint probability density by just this matrix element basically. It's just the diagonal term of the density. And what we find is that in the time t going to infinity limit for this system also, this joint distribution goes to a steady state where the steady state distribution is given by that. Okay, so where sigma is this guy, and this h of u is given by this. Okay, it looks a bit complicated, but okay, you can explicitly find this. You can find the correlation function again and see that these are positively correlated, and these are all-to-all correlations. So I'm keeping this thing, okay, this logo basically whenever I put this one, you should understand that I'm talking about the quantum problem, and if I put this other diagram, this is about the classical problem. So To summarize, basically we have engineered two systems, one is classical and one is quantum, and by this simultaneous driving, and this driving protocols are different in these two cases, but in this driving you can basically drive the system to a steady state, and when the steady state has this CIID structure, and given this structure you can of course compute many of these observables. Okay. For example, you might be interested in average density profile. Okay, so how does the density profile of the gas looks? Okay, so this is simply given by that. This H of u depends on the problem. For example, in this classical case, this logo means the classical case. So let's consider driving where this Z of t is a dichotomous process. Basically, it just varies between two values. So you just tap center is just, it can just takes two values basically. You just keep shifting. So in this case, you see that actually this density profile shows very interesting behavior. In fact, we can have a phase space where there is an active phase where this density profile has these two bumps kind of thing, or you have a passive phase depending on this parameter where it has a bell-shaped curve, and then this is the one in the boundary. So you can find that, okay, basically this second derivative vanishes this thing, and then you have to go to the. This is the quantum case again, depending on, okay, either you fix sigma, which or change the resetting rate, or fix resetting rate and vary sigma, and you see that it has a rather nice transition from a single bump to a double bump structure basically. Okay. Order statistics again. So you can find this order statistics for, as I said it, okay, so if you have this position of this particle, and order means that, okay, M1 means the rightmost particle, M2 means the next one, and so on. So if you just so these are the ordered positions. So you can ask what is the distribution of this kth maxima. So in general, for any kth maxima, what we find is that the distribution is given by this H itself. Okay. So to contrast it, you remember that, okay, for a IID random variable case, the distribution of the maximum goes to one of the three well-known distribution, either Frechet, Gumbel, or Weibull. But this distribution is very different from those distributions. So this is a strongly correlated system indicating. So where this Lk is basically given by this, where alpha is basically k by n when it is in the bulk, and this is at the edges. So these are some examples. This is again this dichotomous noise. So you see that this order statistics for any k, when you scale it, they all collapse to, so this different alpha mean basically different k. Right? So they all collapse to nicely this one, these three curves in these three regimes of this new. Okay. Order statistics for bosons, again you see that, okay, it's basically, okay, it's all collapse to a nice curve, and this is basically simulation versus the theory. Okay. Gap statistics, again we find that the gap statistics is an exponential distribution where this characteristic length ln or characteristic gap can be explicitly calculated. Okay. So again you see that, okay, this is for a large number of parameters both in the quantum and the classical cases, they nicely collapse to this exponential distribution. Full counting statistics, finally, so we are asking the distribution of the number of particles in a region minus NL plus L. So we find that it has this scaling form. So NL by N is the fraction of particle within that box. So this kappa in general can be between 0 and 1 because this is a fraction of particle. But interestingly, what we find is that there is a upper bound kappa max which is strictly less than 1. Okay, so you cannot put all the particles within that region basically. It's almost like some strong repulsion, and it has a square root divergence at that point. Okay, so these are some representative examples. So this is the classical case. So where, okay, this is the dichotomous noise case, and see that this is a square root divergence here. So in this case, actually, when the kappa mean has a bound which is not strictly greater than 0, but if you have a Ornstein-Uhlenbeck drive, so kappa mean is 0. Okay, I'm just done actually. And then on the other hand, the right side is always a kappa max is actually strictly greater than 1. So full counting statistics of actually bosons is very interesting because it has this two pieces structure. Okay, so first of all, kappa max is always strictly less than 1. That's a generic thing. And kappa mean is also strictly greater than 0, but it's very close to 0 so that you don't see it. But what you see is that, okay, it has a square root divergence here, it has a square root divergence here. But this one, this is a discontinuity. If you come from the right side, it fixes to a constant value, but on the left side, but if you go from this side, it has a square root divergence. So to conclusion, basically we have engineered two strongly correlated gases where correlation between non-interacting particles emerges dynamically, and we have a joint distribution of this thing which has this CID structure, and this structure allows the calculation of many of these observable explicitly. And I was talking about, okay, this engineering and experimentally feasible thing, but can one actually do experiments on this? And so this is something actually at my colleagues at RRI, they are doing it at, and they actually can do this in this cold atom system, and you see that, okay, these are still preliminary data, but you see this, okay, you have a single bump versus this double bump depending on how you shake that traffic. Thank you for your attention.
Thank you, Sanjib.
In your final conclusion slide, you have this product form integral with du. But can one do a functional integral over u of t? That will be slight generalization of this. There is a control parameter u of t which varies with time. And
yes.
Now you do functional integral over the probability of that particular profile.
Yes.
Does that extend this analysis somewhat, or is it identical?
It does in some sense. I don't know whether you meant this one, but okay, in the classical case at least, so yeah, in this case at least this u is also a time dependent variable and we can find it at full time, but this is still a single time property. I guess what you are asking is that basically like a functional of the time, and yeah, in this case probably one can do it actually. Okay, yeah.
Thank you.
But yeah, it's like a full path integral.
In the quantum case, if you do the same thing you did classically, that's
we are doing actually. That's a bit harder problem. Actually, we started with that one,
okay.
Right? And so then this protocol turned out to be simpler than that. But that one we are doing. Basically, whatever the same thing we are doing classically, you also do it in a quantum. You can write down the equations actually. So we have the equation.
But it's not clear if it will have this structure.
So that we don't know yet. But so what we know is that, see, this for any time it remains Gaussian. So that's why you can do that, because the propagator is Gaussian, right, in a harmonic potential. But then this soon this whatever the shift and this thing, it becomes more complicated basically. Like it's a Gaussian with around some mean, and then this mean, how it evolves with time, it becomes a bit complicated. That's what we actually started with that problem.
Hi Sanjib. So this quantum problem of the quench of the harmonic trap. So the quench and resetting and back and forth. Can I think of that as a sequence of instantaneous quenches starting from the ground state of a harmonic trap?
Yeah. So what we are doing is basically you start with a ground state of a different harmonic trap.
Yes.
And you are evolving in a different harmonic trap. So you quench to the ground state of this harmonic trap.
Right.
And then you evolve on that red harmonic trap basically. So
but the reset also, I can think of that as a second quench or not?
It is a second quench. It is a second quench.
So now my question is that, you are starting with a free system, right?
Yes.
So if I think of this as a quantum field theory,
yes,
I seem to remember that in a quantum field theory, even if you do a sequence of quenches, Wick's theorem remains true.
Here, when you quench, then you cool down the system. That's cooling down the system is not a unitary operation, right? So it's not only quench. So when I say resetting to this ground state, see, because otherwise if you take it there, put it there, evolve, and then you bring it here, the system will not come to the ground state. To bring it to the ground state, it has to be an open system.
I see.
And that is not a unitary operation, and that these people in the this cold atom community, they can do, and they can actually cool down pretty fast. So in principle, you should actually take into account the time of cooling, and that one can actually extend it.
So I see. So you're coupling to some external system, and you are integrating that out. As a result, some interaction is coming in.
Exactly. You're coupling. So So this this resetting part is basically quenching to this trap and then coupling to some outside wall, and then you bringing the system to the ground state basically.
I see. Okay.
Yes.
Thank you.
Yes.
Question. So I think, no, maybe one. Let's take the last one.
Actually, you just mentioned it, this time. So, you can imagine that they take some time to come.
Yes.
Like imagine you turned a very short trap on, so then everybody went down to the...
Yes, yes, yes.
So if you take that, you'd still get this structure?
So we have not done, we basically in this calculation we have assumed that time to be 0,
Yeah,
right?
yeah.
But I think one can take this to account the similar way people do in the classical stochastic resetting, right? You assume that, okay, I think, I forgot now who, there is this calculation where you reset and then there is some time you wait before the system evolve, right? And that time again you can draw from some another random variable basically. So you assume that, okay, you quench here after time tau, you quench here, and then there is another time tau 1, let's say, involved to bringing down the system to the ground state, right? And that time again you can take it to be a stochastic variable with some distribution, and I think one can probably do the calculation, and I believe that this structure will remain, but okay, we have...
Both in classical and quantum.
I think both in classical, but I have not done the calculations.
And
so
the only constraint is that they should all land there simultaneously.
I mean, it doesn't actually land there, right? Because in this case...
I mean, in the classical case, everybody goes to...
It doesn't go, actually, because classical case, I'm just shaking the thing,
okay.
right? So it doesn't go there.
Okay.
So there is no resetting. I'm just, classical case is even simpler. So because it's very easy for the experimentalist. I have this trap, I have this end particle, and I'm just shaking the trap, that's all.
Okay.
It's like this thing villages people used to do, no? You have this grain and then you just shake them, and it's as simple as that, basically.
Okay. Thank you.
Yes.
Okay, so I think we can thank Sanjib again.
Long live India and France friendship.